Alors, à l'origine, je voulais parler français pour la présentation due à la présence du fait de la présence de certains politiques locaux, mais beaucoup d'entre eux n'ont pas pu venir. Donc du coup, je propose de switcher en anglais, parce qu'il y a beaucoup d'étudiants. Pardon? Oui? You agree? So welcome, good morning, and thanks for attending. Thanks for coming. We do appreciate your presence. So the goal today is just this morning, it's just to present the graduate school, and especially the objectives and the reason why this graduate school has been selected by an international jury. And also my talk will be followed by two talks given by Naomi HALAS and Peter NORLANDER, and to me this is the best way to illustrate the interest of this graduate school, okay? To let world-class people to speak about some scientific points. So I just would like to remind that this project is supported by the French government for 10 years through the PIA, Programme Investissement d'Avenir. So this is, it has been selected by an international jury, and the French government gave us money, okay, to launch the project, okay. And as you can see, there are three main partners: the University of Technology of Troyes, that as you know since yesterday, it is a member of a network, a very promising network of the European University of Technology. And you have also the University of Reims Champagne-Ardenne, so some people are here, and the CNRS as an official partner. So what I would like to do right now is to present the room, okay? I want to present the room. So we had some expected people, but unfortunately they could not attend. Okay, but we have here Jean-Luc Dragon. Hein? So thanks for coming. This is an honor for us to welcome you. Hein? So it represents the city of Troyes, so which is very important to us. We have Anne Jussium. Thanks for coming again. And this is an honor. So you represent le réseau d'établissement Champagne-Ardenne, especially you are the vice president for ethics, deontology. It is very important. There are points we would like to take into account in our project. Obviously, we are our new members of UTT. Naomi HALAS from Rice University, Brian Norton from UT Dublin. They are, since yesterday, they are doctors honoris causa of the University of Technology, so so they are members of UTT now. So we have two new members. We have also so Naomi HALAS also accepted, and this is an honor for us to become the patron of the graduate school, to drive the graduate school, to drive the evolution of the graduate school from USA. And we have also a very important guy, Peter NORLANDER, from the Rice University. He accepted to become a new member of the International Advisory Board. Okay, we've got an international board, which is very important to us to make the graduate school better. We have also Pierre Cor, so the director of UTT. So thanks again for your support. Since the beginning, you have been supporting the project. I remember, I have no time to tell the story, but you have been a very and the member of the board of the UTT, especially the eminent vice director Jérôme Plein, and the members of the direction Farouk Alaoui, no, Thomas Morer. Okay, maybe they are teaching, maybe. We also Kemayes Saanoui, the director of the doctoral school, So I thank him again for his support. And obviously, please raise your hands, the students of the graduate schools. Yeah. So obviously, you are the most important guys of the graduate school, because sometimes we forget that. It seems that we forget that, but actually we did that for you. We opened that just for you. So you're the main members of the graduate school, and I would like to thank warmly the directors or representatives of different partners, engineering school from France, the CNRS, other graduate school in France, because we are not the only one, and we would like to collaborate with some new graduate schools, the other graduate schools. For example, EFI, NanoX, and so on. There are many. And the representatives also of some laboratories, famous laboratories and institutes in France. And obviously the people from UTT, researchers, professors, and so on, people from the supporting service, and so on. Okay. So thanks for attending. So let me now present you briefly the graduate school. So the goal, so this is a 5-year program, okay? In France, the concept of graduate school is not that usual, okay? This is pretty new. This is something the government would like to develop. So this is 3 years for master and 2 years for master and 3 years for PhD. And the goal, sorry, I think I can. The goal is to develop a program of excellence on the use of light at the nanoscale, okay? That is to say, at the scale that is much weaker than the wavelength of the light. And the goal is to train a next generation of researchers, but not only, and this is the challenge, also professionals at the cutting edge of nanophotonic science and technologies. So this is a very challenging point. Why Nano Optics and Nanophotonics? Why did the international jury select this program? As you know, we had in 2015 the International Year of Light all over the world. And it turns out that the light is promising, has a huge potential that is unfortunately not used nowadays. As you said, Brian, yesterday, by the way. And actually, the market is huge. The expected market is huge, more than 600 billions of euros for 2020, including displays, light source photovoltaics, information technology, and so on. And besides, the nanotechnology also constitutes a market, but that is much more realistic than it was before. Okay, and this new market has been assessed. It is more than 100 billions of euros. And the bridge between nanotechnology and optics, this is Nano Optics. Okay, I'm not going, considering people in the room, I'm not going to give a lecture on nano-optics, but I just would like to stress the fact that we study light and light matter interaction at the nanoscale, that is to say at a scale that is much weaker than the wavelengths of the light. Okay, light is a wave with a wavelength, and we study light at a scale that is very weak compared to the wavelengths of the light. And actually, this branch of optics started in the 80s. So this is very recent, if we consider the history of science. This is very recent. Some of people in the room I do recognize did participate, belong to one of the first generations. Personally, I had the chance to participate in Paris in the beginning of nano-optics, of the development of nano-optics. And it turns out that it is a growing topic. and a perfect bridge between optics and nanotechnology. And a first market actually has been assessed. The first market, I've got the number, more than 60 billions of dollars in 2022. And I think we are about to live a pivotal time in the nano-optics history. So I am pretty sure that in the next decade, at the same time, we are going to continue making science, high-level science, but also we are going to start applying nano-optics, as, for example, shown by Naomi yesterday. And light, I would like to stress the fact that light is highly promising for sustainability. This is a message I like giving. Let me show you this graph. The distribution of primary energy supply until 2019. And it turns out, can you see light? No. Actually, light is hidden here. Okay? And emergence of new technologies, including solar technology, representing about 2% in 2018. So there is a lot of work to be made, and it's up to us, especially the students. Okay, the students, to me, will have a kind of duty, I don't know, but exciting role to take part. I just would like, this is not a complete list, I just would like to stress the fact that the use of light will help us to face energy crisis. I just put a list of examples, okay? But I'm pretty sure you have other examples in mind. Photovoltaics, for sure, photothermal technologies, photochemistry, photocatalysis, as shown by Naomi yesterday. Optoelectronics, okay? It is likely that maybe in some, it is hopefully in a decade, we will have photons in the computers, in the smartphones, to replace or complete electrons, in order to decrease the energy consumption. And for example, regarding the big data management and the signal processing, no kidding, and the digital field in the global energy represent more than 7.6% as an expectation in 2025. So this is huge, actually. That represents a lot of nuclear factory. So this is why it is relevant and topical to develop new technologies based on the control of light at different scales to address these issues. So this is. I permit myself, okay, to take a picture. Light in building engineering. I did like this point. So as you can see, people from EPF, l'École Polytechnique Féminine, Eric, they are very aware of that. They are light used for building engineering as a for example, for good mood, for vitamin D, and so it's very, very important. The daylight is of importance, and I would be very happy we would be very happy to take part in the use of this daylight, for example, for new photovoltaics configuration, for smart windows, and so on. Now, what about the partners? The leading institution is the University of Technology of Troyes. So this is a young and dynamic university. As you know, this is an optimized mixing between engineering school, grandes écoles françaises, with the university. So we strive to take the best from the two systems, okay, to optimize the. So this is a pretty small but cute university. As you, I'm not going to read all the information. And we've got 5 research laboratories, including the L2N, that is the leading laboratory. So its director is right here, Christophe Couteau, the new director of the new. You started 1 year ago, more than 1 year ago, 2 years ago. So times is running out. So this is a very an excellent laboratory. About 100 people work hard on nano optics through 6 axes of research. And they, within a global approach of nano optics. Especially people strive to observe, to study, to understand light at the nanoscale through a lot of tools, including numerical and simulation, instrumentation, and material growth, and so on. Sorry. Alors, our local partner, official partner, is the University of Reims, Champagne-Ardenne. So it is much bigger than UTT. It is much older. How old is the university? You didn't? How old? You know? At least 2 centuries? No, 1 century? No, I don't know. But this is a classical historical university with many students. This is in nature. This is a pluridisciplinary university. And they have many excellent laboratories, including 6 of them that decided to join us. And let me give the list. This is very important to us, and this is complementary to L2N. I'm not going to describe all the laboratories, but you can just read the title, okay, the LRN. So we have some representative LRN. Louis Giraudet is the vice director of the deputy director of the LRN. He is also the deputy director of the graduate school. So they are experts in biotechnologies based on QDs, for example. They are experts in nanoelectronics and so on. We have also biospectroscopy. You have some representatives here? No? We have FAR, Agricultural Resource Fragmentation and Environment. And what you understand is that it is very important because they can offer us a framework for application of nano-optics. We have also MEDIC, so MEDIC, some representative in the room. No, we have CEBIO, okay, and we have also thème. We have some representative for sure, yeah. To work on materials for mechanics, for building, also building engineering, and so on. Okay, so basically, this partnership is very promising, and it offers us a very exciting framework, okay, for science and application. We have also officially the CNRS as a partner. So are the CNRS representative here? No, they could not come finally. This is a pity because I wanted to thank them. Because initially, you know, the CNRS, the famous CNRS, selected some projects. They provided some support later to some projects, and it basically made a difference for the final selection. So this is. So I'm not going to present the CNRS in detail, but. This is very well known, especially they have more than 1,000 laboratories and 33,000 researchers. We have many CNRS researchers in the room. And this is, it includes many fields, all the key fields actually that are addressed nowadays. Now, let me now give you some details about the graduate school. So this is a 5-year program, but with many input and output. Okay? To me, students can join us can join us here after a French licence or a foreign bachelor. And we expect to have 25 students. The M1 students, can you please? Yeah. So we have right now we have 5 students, excellent selected students, but only 5. So this is the challenge to fill up this box. We expect also 40 students at the second year of the master, corresponding to the students coming from this box, and also new students, especially the students from the University of Technology of Troyes, who want to prepare a double diploma, a double graduation, to get both the research master diploma and the diploma from UTT of the Ingénieurs Grandes Écoles, which is very highly appreciated by the companies in France. And we want also, so the M2 students, please, the M2 students, yeah. So right now, we are more lucky, we have more than 15 students, M2 this year, mainly coming from UTT and from overseas. But this is the challenge, and as you can imagine, I never like complaining. As you can imagine, this is not the best time to start an international graduate school due to COVID crisis. We had many cancellation, many, I don't, but it is, hopefully this is about to finish, thanks to the vaccination in particular. And also, so this is very important, after the master, hopefully they can get a job. This is a challenge. That means that our duty is to provide some skills that are compatible with what is expected by companies and so on, okay? And this is a pure challenge in France. I don't know if Ireland or USA, after the master, to get a job, this is a pure challenge. But at UTT, we are familiar with that, okay? We form a lot of engineers for industry, so we are pretty familiar with that, and I'm pretty confident. And this is an asset of the project, to have an engineering school involved. And we have finally 3 years of PhD. We expect 90 students, 30 students, 30 students, 30 students, that are expected to prepare the PhD at the L2N, but also obviously in some laboratories, maybe in part-time, all over the world, corresponding to a network of collaborators. And 4 doctoral schools are involved. The SPI doctoral school from UTT, led by Kemaye Saanoui, but also 3 other doctoral schools from URCA, from the University of France. So what about, obviously I'm not going to describe in detail the program, but this is the curriculum, this is the program of the graduate school, the current program, but this is expected to, it is flexible, it can vary depending on the participation of anyone. But basically the semester 1 takes place in Reims. Okay, the beautiful city of Reims, historical city of Reims, when the king of France became kings for centuries. So basically, in that case, the goal is to provide basis, okay, on optics, solid-state physics, mathematics, and computing. And very important point I would like to stress, they have a first lab project corresponding to 1 day a week, corresponding to 6 European credits. So they can choose in the list of projects proposed by the different laboratories involved. After the semester 1, the students move to Troyes. This is not a long trip. They are supported by the graduate school in terms of lodging, in terms of facilities, and so on. And they join UTT to have this training, okay, to learn about different points. So it becomes more and more nano, for sure. Especially, they have a first lecture on Nano Optics and Nanophotonics. They can learn about microscopy, spectroscopy, nanomaterials, and so on. And also classical and quantum light-matter interaction. In the first semester, there is no light-matter interaction, mainly the optical wave optics. And here, they can learn about the local interaction at different scales, and also they learn about optical materials. And again, very important, two important points. They have a new lab project for 1 day per week, 6 credits, and they have a very important course about innovative companies, entrepreneurship, economic intelligence, and so on, by some experts. The semester 3, they stay in 3, and it becomes more and more nano-optics through, for example, multi-scale characterization, hot topic in nano-optics, to summarize what is currently very topical and very promising. So it can change depending on the actuality. And very important, look, management of research project, for sure, to teach them how to manage a project, which can be very useful even if they decide not to become researchers. Management project, it includes everything. How to manage people, how to understand people, how to recruit. It's difficult, as you know. How to take into account the different cultures, how to get money, how to apply, how to manage, and so on. How to hire people, and what about the work packages, how to define them, and so on. And very important, a new lab project, 12 credits, 2 days a week. 2 days a week. So it can be a new lab project compared to the previous one. It could be a new lab project, or it can be a continuation of what they did so far. And finally, the last semester is a 6 months internship in a laboratory or company belonging to our network. And finally, if you count, and if you take into account also the management of research project, the research corresponds to about 50% of the training of the program. And after that, they can defend a master thesis. Okay, this is new in France. This is unusual in France. A master thesis corresponding to not only the internship, but also to the different lab projects they had. And actually, the students are expected to build their project. So this is very important. Now, regarding the partnership, it is expected to be very important to increase. I only put some examples here of very close universities, laboratories that are partners. We signed some agreements. We expect to have many exchanges from all over the world. And we have also in red, we have also some companies. Some companies, maybe you recognize some of them. Okay, Atos is very well known for communication and communication signal processes and so on. Suris, we have a Labcom in Suris with Suris. Gilles Lérondel, he's here. He's Gilles, yeah. So Gilles Lérondel is the coordinator of this Labcom between Suris and UTT. It is about optical way of for security, okay, for bills, passport, and how to use nano optics for proposing new technologies for security, for photonic security. So Actually, this network is expected to get stronger and stronger. And we would like to extend the partnership, and also not only overseas, but also in France, especially with some people who are in the room, okay? So I had the opportunity, to discuss this point with some of them, with some nice glass of wines and glasses of wine, as you know, since yesterday. And obviously, and this is a very important point and challenging point, we would like to rely on this new network, the European University of Technology, to share the graduate school and to have many exchanges of students and faculty members within this exciting frame. So, let me stress this fact, regarding the interaction with socioeconomic players, let's take part in the development of the market, and actually the domains of application of Nano Optics are very numerous and challenging. You can recognize for sure some hot topic, security, health, sensing, data storage, lighting, sustainability, energy, and so on. We will have some examples after my presentation. The scientific challenges have been defined. They are very general. It's about materials. Now, materials, it is about functional nano devices, okay, for application. It is about also, still we have to study science, because fundamental phenomena in nano-optics are still to be discovered and so on. And nanofabrication for nano-optics. And I would like to stress this point. This is not, to me, like we said in France, this is not tarte à la crème. I don't know if you know this expression. This is not a tarte à la crème objectives. Tarte à la crème objective that is, okay, you just blah, 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 blah. But to me, this is not only blah, blah, blah. We really want to develop a global approach to address, obviously, science and technology, but mainly, as for example, Naomi HALAS does. So this is, she's got an inspiring approach, application for society. So to me, this is the very, very important point to be taken into account. And obviously, mainly, environment, sustainability, and ethics, gender issue, and so on, okay? We belong to a society. We are not only scientists, we belong to a society, and we have to serve this society and to take into account the expectation from people, especially from people who pay. So basically, the people. In France, and we are a public school here. So, and the funding we have is public as well, so we have to bear in mind this point. Okay, this is my last slide. So this is also a challenge. How to develop a modern way of teaching. Personally, I don't know, we have many teachers in the room. I'm fed up of lecture, tutorial, practical works, lecture given by a famous professor, tutorial given by assistant professor, practical works given by, insured by, we want to mix everything together, especially from integrated classes, okay, where we mix a fundamental presentation, experiments, exercise, tutorials, and so at the same time, to make a lecture exciting and funny. We will also to make sure the personal project will be developed. So students, I have a message for you. This is up to you to build your project. Okay, we are here to help you, okay? We are here to propose you a program, a frame, but this is up to you. This is up to you, really, to bind your project, to propose something, we would like also to use modern tools like immersive rooms. For example, we have this. So this is a concept inspired by Centrale Supélec in Metz. They gave us this concept. So this is a room for sharing ideas, for sharing experiments, where you have many guys living in the room, students, visitors, professors, engineers, and so on, to meet and to share. Virtual reality, we would like to get some module of virtual reality in optics especially, and in electronic microscopy. The concept of e-lab also, to enjoy the lab from overseas, for example, from abroad. So this is why not using serious games, okay? To fabricate a SNOM, scanning near-field microscope. The experts are laughing, are teasing me, no? No, why not a serious game? We had many ideas in mind. And mainly a very important point, the students will have the opportunity to use the facilities we have, especially the 1,000 square meter platform, a Nanomat, you visited yesterday. And so the students are expected to enjoy this room daily, these laboratories daily. Okay, so I have to stop. So thanks again for your participation, for attending, and for your attention. And I would like to thank especially the people who helped us to prepare this day, especially the communication service. I just put two names of so Delphine Ferry. Delphine, tu es là? No, she left. Ludivine, she left as well, no? Okay, but the communication service and her director, Léonore Manon, did help us very much, okay, so I would like to thank them. The technical service people, and Angélique Bavasso and Angélique, yeah. Thanks, Angélique. Angélique Bavasso, the assistant of the graduate school, for the help. Thanks a lot for your attention. And now the best, as I told you, the best way of illustrating the interest of this graduate school is to make excellent people speak about some parts of Nano Optics. So the first speaker is going to be Naomi HALAS. Thanks. Let me.
Good morning. It's wonderful to be here, and I must add, very good, that we look forward to adding Rice University to your list of university contacts and networks. We would love to do that. So I'm giving a completely different talk than yesterday. This is some other examples of how nanophotonics can be realized in very broad ways. So this was actually the title for yesterday, but one of the organizers put this on my title for today. So I'm going to give you I'll talk about two topics today. And each one has its own title. So the first topic is desalination and how we can look at solar methods for solving one of the big global problems that we have. Of course, we live in a century where we're looking at really large global problems like climate change, of course, and population, disease, public health. Many of these are very important issues, but what is so exciting is that this is our century. The people who do photonics and do optics and engineering, working together from different fields to solve some of these very complex problems. So I'll give you a couple examples today, and this is the first one. Let me introduce some of the people who are involved. So I have collaborated with Peter NORLANDER in his research group for about 20 years. So he's also involved with this work on the theory side. Alessandro Alabastri came from Milan first to work in Peter's group, and now he's actually a professor at Rice. It does extraordinary work, and it shows you the power of numerical modeling of very complex systems in understanding and really capturing the potential and capabilities of systems as complicated as water treatment. And also Pratiksha Dongari and Owara Neumann one is a postdoc, one is a research scientist. They are the experimental arm of all of this work. So they're the builders and they're the demonstrators of all of this, all of the work I'll talk about today. So this is the problem that I'm talking about. This is a huge global problem. It's not a problem locally, I see. There's plenty of water here. But as you know, there's large regions of the planet where daily water is a huge problem and clean water is a huge problem. So the issue of diseases, and of course, the most susceptible population that's in need of clean water are children and infants, because they're the ones with the highest mortality rate due to waterborne diseases. So if you look at the normal way that people have technologies that exist for clean water, have something in common, and that is that they almost always use a lot of energy. So this is one of the major challenges in many parts of the world where there is a need for clean water. You also have a very unavailable or a lack of reliable energy resources. So how can we combine those two? How can we deal with those two challenges? And the answer is simple. How could we begin to utilize solar energy intelligently to solve the problems of desalination? So let me introduce to you a technology that's been around for 40 years, and this is called by civil engineers a technology of the future. So this tells you right away, when somebody tells you something that's been around for 40 years is a technology of the future, it needs some true innovation to make this happen. So let me explain this to you. So this is, so it's called membrane distillation. And what you do is you put in salted water, saline water, on one side of a membrane, and this has a temperature greater than the other side of the membrane. So this temperature difference leads to a vapor pressure difference. It only needs to be about 5 degrees, 5 or 10 degrees. And what happens is when you have this temperature difference and this vapor pressure difference, what you have then through this hydrophobic membrane, you actually have water that evaporates on one side of the membrane and condenses on the other side of the membrane. So of course the evaporation and condensation process leaves the salt behind, and so this is a way this is a desalination process. But you can see immediately what the problem is and why this takes so much energy, because you have to heat all of the input water. And the heat capacity of water, as you know, is very high, and so this leads to the very large energy consumption. So what is our answer? So our answer comes from some sort of crazy experiments we did a few years prior to thinking about this problem, and that is generating solar steam. So let's talk about how we make steam. Everyone who makes coffee or tea makes steam. You start with water, and then you put it on a heat source, and then you wait because of the heat capacity of water. And once you wait, right, so you're putting in a lot of energy to heat that large volume of water, and then eventually you'll make steam. But if you're in a hurry, what you can do is take water, put in nanoparticles that absorb light, and then you can shine light, in this case sunshine, onto the nanoparticles. If they absorb across the solar spectrum, what you'll get is you'll get steam produced immediately, with a very high efficiency, even if the water's in an ice bath. So you can have cold water at 0 degrees Celsius and you can make steam at the same time. So what's going on here? There's no new physics here. It's just a very simple property of the way nanoparticles interact with light. So I'll show you, this is what the experiment actually looks like, and it looks like a high school science experiment. We're really using sunlight, not a solar simulator. So what we have is a little beaker of water that sits here, and it has a thermocouple inside, so we can measure the temperature of the water. It's sitting in, I'm losing my cursor here. It's sitting on a mass balance, so we can measure the steam that's produced, and at the same time we can measure the temperature of the liquid. And so then if we look at what's actually going on as we sit and irradiate with sunlight, so we find, of course, with fluid heating, if I have a larger volume, then the heating is slower, right? But unlike what we would expect, we find that, of course, the steam that's generated is, and these are the efficiencies, right? So the steam that's generated is generated independent of the volume. So how could this be working? It's very simply because this is an effect that has to do with the way that energy gets localized when I have a solution of nanoparticles, relatively dense solution of nanoparticles, that both scatter and absorb light. So as each photon comes in this concentration regime, each photon can scatter once, twice, multiple times, and then be absorbed. So I have a regime where I have multiple scattering events coupled with absorption, because that's how we raise the temperature. But what this does is it localizes the light energy to be just at the surface, which is why I can put the solution in an ice bath, but I can at the surface, basically a surface effect. It's an interface effect. And this is an example, so this is actually a calculation, but if you do this experiment, you can actually take photographs and they will actually match the calculation. It's a Monte Carlo calculation where we're throwing in 1 million photons because we're in this scattering and absorption regime. So this is a histogram of the scattering events before absorption. What are these? So these are basically like a little cuvette in a laboratory, and the difference between this one, the difference between the one on the left, the center on the right, is the concentration of nanoparticles. So we go up by a factor of 10 and then another factor of 10. And you can see exactly what happens with where the light energy goes. Here we have basically propagation of light about halfway through. This is essentially Beer's law with absorption. But when we have multiple scattering events, we deviate from Beer's law, and we have a concentration of light energy right at this interface. So that for something like membrane distillation, right, this effect could be very, very useful. Right? So we trap the light in the very small volume into the surface region, and so we can use that accordingly. So how does this translate to membrane distillation? So we take the same membrane that I showed you before, but on the surface of the membrane, we put a layer, a porous layer, in which we have absorbers. Now, we don't want to use gold or silver or something that's very expensive. Here we use carbon black, which is a very, very inexpensive material. It's essentially graphene in amorphous form. We have in this regime, this layer, we have exactly that same scattering and absorption effect. So what this means for desalination is that the input water is not heated. So we start with cold input water, but then we have sunlight. When sunlight heats this membrane, the water at the surface of this layer then becomes heated as it goes into this region. And so we have a very localized heating, which then gives us a temperature difference that goes across the membrane, and then we can have evaporation on one side and condensation on the other side of the membrane. And so we call this, so now we've converted this to a solar process, and we've eliminated the heating of the input water other than through sunlight. So now we're using the power of the sun directly. We're not using photovoltaics to heat things up first. That's a much less efficient process. But here we're using direct irradiation to establish that temperature difference and to cause the desalination. So we call this nanophotonics-enabled solar membrane distillation. This is the way the units look when we build them. So we use just a small window, but the idea is that you would eventually have a solar desalination panel, like a photovoltaic panel. You could have a desalination panel. So we did our first experiments this way, and Alessandro modeled the system for us, and you can see the difference between, if we just look at this as a simulation of what was going on in our unit. So the salt water comes in here, and then the light is absorbed here, so the heating happens here, and the water transmits through the membrane and it exits out here. So the feed is the input water, the permeate is, or the distillate is the output water. So if we just look at the temperature profile for the conventional approach, you have to have delta T at the beginning of the transition, right, of the feed across the membrane. So delta T is always going to be the highest at the beginning, and after a while, delta T goes to 0. So it doesn't matter how large you can make the membrane, it doesn't scale, right? Once delta T goes to 0, nothing happens. But here, as the water progresses across the membrane, it's being heated by the light. So the larger you make the system, the more water you're going to be able to distill. So we see this progression here. So this scales up, where the conventional system doesn't scale up at all. So the process scales up. It's actually very efficient at relatively slow fluid velocities, where the conventional system, you have to get the water going as fast as possible. But here, it doesn't have to go fast as possible, which means you don't need you can use a simple type of solar pump. And it's also quite efficient at high temperatures. So the next step, what's the next thing that we could do? So we did something here that, so this again, this is what I just showed you, NESMD, but we're putting a lens array on the surface. So if this was so you'll notice you've never seen a solar cell that looks like this, because the photovoltaic effect is linear. And this is a great way to reduce the efficiency of a solar cell. First of all, in two different processes. First of all, we're focusing light into tiny little spots, which means that most of the surface is not irradiated at all. So the light only goes to very tiny regions here. Plus, because the light's being absorbed, you have large photothermal effects. So if this was a solar cell, this was a photovoltaic cell, both of those things would decrease the efficiency. But here we see something very different. So we are using I'm sorry, this is 25 millimeter and 50 millimeter lenses, not centimeter lenses. So it's a small array. I apologize for that. But this is, so let's see what happens when we do the desalination with this. What we see is in fact, that the efficiency goes up. And it goes up pretty substantially, as much as 50%. So what could be going on here? So just by focusing the input light into these small spots, we increase the efficiency quite a great deal. Well, this tells us a lot about the behavior of this kind of system that's, in retrospect, is actually obvious, but really no one had been thinking about this system this way before. So as I said before, this depends on the vapor pressure difference, or essentially the saturation vapor pressure of water. And these are some simulations again, from Alessandro Alabastri. And so the distillation process is an exponential function of temperature, right? It's a phase change process, an exponential function of temperature. But photothermal heating, in other words, the temperature increase as a function of light intensity, is linear, at least for the first 100 degrees. It's linear. So put those two together, and then you realize that the distillation process is actually exponential with light intensity. So this is why when we focus light, like any other nonlinear optical process, but it's a very nonlinear optical process, then the performance, the amount of distilled water, the distillate flux that we get out of this system goes up tremendously when we're able to do this. So we looked throughout the literature and we thought, how do other people, so people use solar collectors when they do solar, and other people, of course, are making different types of desalination processes. At this point with solar, is an idea that really has caught on globally. So we looked around the literature, and how do people increase the amount of flux? They make bigger and bigger and bigger solar collectors, and no one thought to put a lens on. So these are just some random references, and you can see the light intensity people are increasing. So light, daylight, noon, on temperate regions of the planet is 1 kilowatt per meter squared. So if I go above 1 kilowatt per meter squared, I'm collecting a large area, or I'm focusing the light. So this is what we did, right? Our system size never changed, but we're increasing the solar intensity by light focusing. In fact, we're actually throwing away some photons because we have reflection off of the lenses. But this is a way of making a system much more compact than these other systems, but increasing the efficiency. So one other thing, so we can talk about one other aspect of this system, and that is adding a heat exchanger. So why would we add a heat exchanger? This is things that people in optics and photonics don't really think about at all, but photothermal aspects are always very important. So here where we're heating water, of course we're evaporating, so we lose energy on the input side, and when we condense, we transfer that energy to the distilled water side. Right? But we want to always, so that's in opposition of the temperature difference that we're setting up. So we're decreasing the effect just by the effect itself. So we're adding hot water to the distilled side. So if we could transfer that energy back, transfer the thermal energy back to the input side, we could make the process more efficient. And so it's actually really simple. So this is the membrane. So all we do is we add a little copper plate onto this system, so where we have the solar exposure, and so solar heating, we have evaporation and then condensation, and then this now it still has this latent heat from the evaporation process and condensation process. And so now this, as we have a heat exchanger, this then transfers the heat to the input. So this makes it more efficient. But it also gives us a very interesting and surprising effect that we didn't anticipate. And that is that the efficiency shoots up enormously when we do this. And it shoots up by a factor of 5. So all of a sudden, we've increased the system by 500%. So what is actually going on here? Let me show you again some simulations that tell you what's actually going on in this system. So if we have a fluid, so the fluid flows have to match. So if we have, in the case of for example, the fluid flow much faster on the input than on the output, then the energy dissipates. And it's the same way if we have the fluid flow slower on the input than the output, then the energy dissipates. But if we match the fluid flow, but also to the light intensity, we end up with with an actual coupled oscillator effect where the energy is kept inside the system and exchanges back and forth. So we've now built something that we call a thermal oscillator, and it's essentially an energy storage device. As it is desalinating the water, it also stores energy inside of the system. So what does that mean? That's actually very exciting. If you look at what happens over the course of many days, we have, so this is a simulation matched with experiment. Let me show you a little bit more clearly. Okay, so let's slow this down to just a couple days. So what happens when I have this heat exchanger? It acts from an electrical point of view, you could think it's like a low-pass filter. So of course this is a nonlinear effect, so every time a cloud passes over the system and decreases the light intensity just a little bit, we see big changes in the amount of distilled flux. Okay, so that's what all these spikes are. These spikes are just clouds passing over. And of course with the solar cell you don't see this, but here the system is nonlinear. So we have all of this, all these big variations in the flux. But when we have a heat exchanger, it integrates over that, so we don't see these very large changes, which is nice. But what's really nice is what happens when the sun goes down. So what happens when the sun goes down, because we've been storing energy, we can keep on making clean water. We can make clean water almost the whole way till sunrise. So this also is a very exciting way to combat one of the basic problems of solar, of harvesting solar energy, and that is, what do you do at night? So I think this is also a really interesting paradigm for how we can begin to think about using solar sources in more intelligent ways. So on to another topic. This is a topic that really is, there's of course some absolutely beautiful work being done here in aluminum. In our case, I'm going to talk about a certain subset of aluminum work that we've been doing that really ties in more to chemistry. How can we grow aluminum nanoparticles? Because of course, if we look at applications of plasmonics, applications historically, people have done a lot of work with, of course, silver and gold, but if we look at the abundance of these materials on Thank you, thank you. That's okay. Okay, so if we look at the abundance, very good. So if we look at the abundance of all these elements on the Earth's surface, we see, of course, large variations, orders of magnitude between some of the most abundant elements and some of the least abundant elements. And of course, we know that gold and silver are rare. We also know that many catalytic materials are extremely rare. So in contrast, aluminum is the most abundant metal at the Earth's surface, but it's in oxide form, of course, so that's an issue. But it's even more abundant than carbon, for example. Right? So this is always going to be very plentiful, and in terms of its plasmon, aluminum has a wonderful plasmon in nanoparticle form. As you change the size of the nanoparticle, you can actually tune the plasmon from the UV across into through the visible and into the infrared. So it's very attractive properties. But also because of its abundance, it will always be very, very low cost. So when people talk about using plasmonics for large areas, they really cannot be thinking practically about using large areas of gold. They have to be thinking about how we can begin to adapt aluminum and very, very abundant materials into these kinds of applications. So chemists know how to make metal nanoparticles, so it's pretty simple. Because this is a very well-developed field, and people have made, of course, all of these different nanoparticles for decades. So you start with a metal ion, and then you add some kind of a stabilizing agent or a reducing agent. So the typical things, say, for example, I want to make gold, so I'll add something called sodium borohydride as a reducing agent to reduce the gold plus to gold zero. And then I sometimes have a capping agent to control the growth. And then I can make all of these different beautiful colors, and I can take a picture and publish a paper. But if I want to make aluminum nanoparticles, nothing here applies whatsoever to the chemistry of aluminum nanoparticles. So when we started this, we thought, well, how hard could it be? And then we began to realize it is so unique and so different that it is really its own field. But there's a lot we can learn from noble metal nanoparticles, and that is, so if an example of all of these FCC metals, they have many different types of nanoparticle morphologies, all of which have been demonstrated really beautifully within the coinage, gold and silver families. And so how can we actually adapt some of these are canonical morphologies. Aluminum's also an FCC metal. We should be able to start to make several of these types of shapes as well. But sadly, when we go and we look into books and into review articles, and we see all this beautiful work that's been done, and aluminum is just nowhere to be found. So how can we begin to bring aluminum now into this family of FCC metals that is intelligent? So we began by adapting a protocol that was developed by an inorganic chemist for making aluminum nanocrystals. And so there's a couple things that were absolutely unique about this. So let me explain a little bit. So first of all, nothing can be done in water because it's a very very active, literally explosive oxidant, right? So this is so aluminum oxidizes very intensely in the presence of water. But to make these nanoparticles, first of all, requires a catalyst. Nobody else has ever used a catalyst to make a nanoparticle, so this was something that was unique and surprising to us. But this provided a route to get to making uniform nanoparticles. But then how do we control size? So my student, Mike McLean, made a very interesting discovery. So he tried to make nanoparticles using one solvent, this is dioxane, and he made small particles. And then he tried to use another solvent, this is THF, and he made another size, big particles. And so he thought, well, let's just mix the two and we'll make particles of intermediate size. And that worked actually pretty well, right? For a first pass, if we only care about the optical properties, we can actually map out the optical properties really quite beautifully. And this is the way the particles are icosahedra, or they're dodecahedra. They always have a terminating oxide that actually protects the particle from further oxidation. So they're very air stable, more air stable than silver actually. But what we also discovered when we began to take single particle measurements and then connect them to theory was Now this should look very strange to many of you, right? The theory model were always broader than the experimental spectra that we were able to measure. These are dark field spectra. And the reason for this is actually very simple. The dielectric function that people had been measuring since they started measuring properties of aluminum was measured with dirty aluminum, because aluminum is very reactive. If you grow a film, you're very likely to have more than 10% of that film be the oxide. So that modifies the dielectric function. It also tells us that we are making remarkably pure oxide when we grow nanocrystals chemically. So it's actually it turns out, so a group in Taiwan was inspired by this work, and they went to a synchrotron to try to grow ultra-pure aluminum films. They found that only at low temperature in an MBE system where the pressure was so low you could not measure the pressure anymore, below 10 to the 13th torr, that was the only regime where they could actually begin to make aluminum as pure as you can make in the laboratory if you grow by chemical methods. So we thought this was very exciting, and then we also began to try to understand what happens in this complex chemical environment. I don't want to get into the chemistry deeply, but just give you a very quick overview that you have a catalyst that's titanium. You start with alane, which is a salt. You have to reduce the valency to make it into a metal, so the metal then can grow as a nanocrystal. And so whether you have whether you have THF or dioxane, it complexes with this sort of the birth chemistry. It complexes a little differently, and that controls the kinetics. So how the solvent molecules now sort of embrace the catalyst, and the first nucleation species will determine whether or not we have large particles or small particles, depending on what is formed here. So we looked quite a bit at how that affects the thermodynamic growth, and you can see in all cases you still have this complex, which then is controlled by the solvent molecules. So, so this was, as our starting point, we're using one particular type of catalyst. And so we spent a lot of time playing around with solvents, and all we really saw was variations in size. And then we decided, let's change the catalyst. So what happens when we change the catalyst? The whole shape of the nanoparticle changes. Now that's crazy, because first of all, it's the first time anyone ever used a catalyst to make a nanoparticle, but then what in the world does the catalyst have to do with the shape? So it turns out that the catalyst molecules also, once they're done initiating growth, they come back and they sit on the surface of the various crystal faces, and they actually control the way the nanoparticle grows, which is a unique thing in the catalysis world. So catalysts do two things, right? Both of them very, very unusual, but the second one is very exciting because it means we can now begin to learn how we can control catalyst shape. So in this case, this was another discovery in the lab. My student, Ben Clark, was trying a bunch of different catalysts, and all of the solutions were kind of looking gray and muddy, but one was beautiful purple. And he did measure, he went to do SR measurements, but then he came back and he said, it's so beautiful and purple. What's up with this? And as he did a TM image of the nanoparticles, he discovered there was a very, very high percentage of cubes, and they're really perfect. They're beautiful. You can see single crystal, all 100 faces, and just remarkably sharp, and with beautiful plasmonic properties, all related to the fact that we're now making nano cubes. So the catalyst actually controls the nanocrystal shape, which was just wild for us. So if you increase the temperature of the reaction, you still have this effect, but the reaction now, the kinetics goes faster. So in addition to making a cube, you find that in this region where you have fewer catalyst species, probably, this kind of our hypothesis, so it grows faster, so we have more kinetic growth on the ends, and so we make octopods this way, just as a variation of the nanocubes. Again, very, very crystalline, but then we have this interesting sort of shape. And we can make other crazy shapes, all using the same sort of catalyst. So we're in the middle of trying to understand what really at the molecular level, how does this catalyst, and how can we vary the catalyst further to make other types of wild-looking structures? And of course, the plasmonic properties, now that we can make nanowires, now go well into the mid-infrared, and so there's lots of other interesting applications that we can envision by having this mid-IR, near-IR and mid-IR nanoparticle that we can make easily. So just in my last, I don't know why that happened. Okay. Very good. Don't know why it happened, but it went away. So in just the last few minutes, I'd like to describe another nanoparticle that we made out of aluminum. And this should be very easy to understand. Tiny, tiny particles will have a resonance in the ultraviolet, which they do. So we make particles that are very small, 20 to 25 nanometers in diameter, not perfectly monodispersed, but pretty well controlled. And so then my student David Renaud, who was working on this, decided to look at the optical properties, and boy, did he make a crazy-looking discovery. As you increase the amount of the concentration of nanoparticles in solution, these are all UV-absorbing nanoparticles, right? So why in the world do they start to absorb light in the visible region of the spectrum? This was a huge surprise for us. And of course, we thought there was something very exciting and exotic going on here, but when you hear hoof prints, when you hear hoofs, you think horses and not zebras. And so we realized it's actually a very simple explanation, and certainly with the help of Peter's group, we began to think more carefully about what are the actual properties of aluminum across the visible spectrum. These are dominated by the interband transition in aluminum at about 800 nanometers. So if we look at the absorption and scattering, in contributions to the extinction, we find that actually in the red region of the visible, into the near infrared, we have a very strong absorption. So the absorption to scattering ratio changes a lot as we go across the spectrum. So it changes from basically very low absorption to very, very high absorption due to the electronic properties of aluminum. Hadn't really thought that this would be important before, but we can see it's actually very, very important, and it pulls up the spectrum across the visible, which means that we can actually start with ultraviolet nanoparticles, UV resonance aluminum nanocrystals, and they're actually very good near-infrared photothermal absorbers. Who would have thought about this? But it's because the electronic properties actually dominate. So this is a solution at 400 nanometers. So we're irradiating the same solution here with blue light, and then with 800 nanometer near-infrared light. And if we measure the photothermal heating properties, they're almost identical in very, very different regions of the spectrum. Very, very exciting and very unexpected result from just the simple electronic properties of the material. And last but not least, so Peter is going to talk in his presentation about photocatalysis. I just wanted to mention since I've just introduced to you aluminum nanocrystals with different shapes, we can do now a very interesting experiment. We take the simplest chemical reaction we could ever think about, hydrogen and deuterium, exchange. So if you take the nanoparticle and you flow hydrogen, H2 and D2 over the surface of the nanoparticle and you shine light, if you produce HD, it is because you've dissociated the hydrogen and the deuterium, and so it recombines, and this indicates that you actually have a hot electron process that happens also on aluminum. And here also, this process is dominated by visible light because the absorption due to the interband transition is so very, very strong. So then we thought, let's do a crazy experiment. Now that we can make particles of different shapes, does the shape actually control something like this photocatalysis? So we have particles that have, so of course we started with the nanocrystals, and then we have the nanocubes we can make, and then we found that we could make octopods, and they have very, very similar plasmonic properties. The main difference is, in fact, the morphology. So does it matter? Turns out it matters quite a bit. So we're not going to talk about all of these. It's just mention that the octopods are way more reactive than the nanocubes and the nanocrystals in terms of dissociating the hydrogen and the deuterium. And in fact, the barrier, if we measure the barrier, so thermally, in the dark, the barriers are the same, but the barrier is lower, substantially lower for the octopods, the pointy particles, the pointy particles compared to the cubes or the nanocrystals. So if we look at simulations, we can actually see that because we have these exposed regions the light penetrates further. The light that penetrates into the metal itself is what is responsible for generating hot electrons. We have far greater generation of hot electrons due to these concave structure of the nanoparticle, then the cube, then the nanocrystal. And so we follow theory really beautifully when we then look at the relative rates of hot electron production for the three different shapes. So we discover an interesting property there. So this is not a finished story, right? We have made, we have identified all different sorts of morphologies within aluminum. We haven't purified them. We don't know systematically how to make them. But we realize that actually a lot of different structures now, even more than you see on the standard FCC canonical shapes for crystal structures, we can make even more unusual structures with aluminum. And if we go back to this chart that had all of the different metals that have all these different morphologies, we thought, where we were already getting kind of depressed, we'll never be able to do this with aluminum. Now we can. Just in the last 5 years, we realized we can actually begin to include aluminum in this table where we already have several of the noble metals. So just to conclude, I've told you a little bit of a story about desalination and how solar desalination is something that we can really begin to see as a process that we can make more and more efficient the way we begin to innovate different types of ways and where we begin to understand the process that's going on better, then we can actually begin to discover new effects like the resonant thermal oscillator effect that I showed you. And also the earth-abundant plasmonics is a field that I think is really going to be increasing as we begin to focus more and more on applications. So with that, I want to thank you very much, and I'd be happy to answer a question. Okay.
Where are the microphones?
They're not here today.
Do you know where are the microphones? No? So please, I cannot find a microphone for the discussions. Okay. So you have a question? Thank you, thank you.
It's the ultimate compliment. Thank you.
Thank you. Actually, the deal is that you talked about processes which enabled to enhance significantly the efficiency of, for example, the desalination process. However, you are using for this nanoparticles. So I would like to raise the environmental and health issue. How do we deal with the fact that the water or whatever fluid it is filled with these particles, and which particles should not, as I suppose, spread to the environment? So have you been dealing also with these issues?
Oh, absolutely. We have been dealing with these. So when we first did the solar steam, that was one thing we checked for, where we're actually producing steam and condensing it in elsewhere. Are we conveying do nanoparticles convey with the water vapor? And they do not. So we were never able to see that particular effect. And we tried this with several different types of nanoparticles. With membranes, we've looked at this extensively. We're actually part of a water center, which has a lot of work on nanotechnology and exposure of nanoparticles. We do, of course, know that silver has unusual properties because silver ions are antibacterial, so there certainly can be physiological effects with silver. Well, we have not seen any reduction of the carbon black in these membranes here. It doesn't leach out of the membranes, so this does not seem to be a substantial issue here. But of course, anytime one deals with nanoparticles in the environment, one wants to be asking these questions. That is absolutely certain. Aluminum is interesting because, as I said, it's reactive, and it does. If you put aluminum particles in water, they will oxidize. Unless you figure out a way to protect them, which you can do, grow silica, grow other structures around them, they will oxidize within a matter of hours. So that actually, they just reduce to the aluminum oxide that we have all through the environment. So that's not, that does not seem to arise to cause health problems. But that's also an open question. We've never had uniform nanocrystals made out of aluminum. So what could be their physiological impact? I actually have a student now who's looking at the effects on bacterial cells and mammalian cells. Are there effects of aluminum on these particles? It's interesting because, of course, we have in our bodies probably about like a sheet of aluminum foil this large. We probably have this somehow because of all the different exposure we have. We ingest things with aluminum foil on them. That aluminum foil gets in our bodies. So we do have a presence of, just the way we have microplastics in our bodies, we also have aluminum in our bodies. So it doesn't seem to induce any health problems that we know of, and we're all being exposed a lot, but it's a very important question that needs to be researched without question. Thank you for asking.
Thank you. Alex?
The aluminum thermometers, which seems to have a better efficiency than 800 nanometer, kind of in a spectrum, to sort of doped your carbon black in order to have a better steam efficiency?
So that's a good question. Of course, we have to, so what we also did when we made the very small nanoparticles is we grew silica around them to see how stable we could make a silica-coated aluminum nanoparticle, and they actually are very, very stable in water that way. So there are certainly applications in that regard. So that could be an alternative. Of course, the solar spectrum, the advantage of carbon is that the AM 1.5 solar spectrum is very broad, and so is the absorption spectrum of carbon black, and aluminum less so. So with aluminum, you might think, so one aspect of doing quote-unquote solar desalination is not using sunlight at all, but using LEDs. Mm-hmm. And that actually is that's actually a very exciting direction. So there's ways in which the technology can divert from solar and go to something that you could have inside your house, but still you could have very high efficient, efficiencies that would be, say, a more energy efficient, but have the same kind of performance as reverse osmosis or some of the other systems that people currently use.
Thank you.
Question over there.
Keep dropping my water glass.
Thank you very much for your talk. And especially the second part remembers me some work in our lab on completely different nanoparticles, which are iron oxide nanoparticles with different application because we use the magnetic properties, but we have similarities on the effect of the shape. And of course, the colleagues are able to get very various shapes of nanoparticles with different interaction with magnetic field when you apply it, and with application in bioimaging. You have shown us, and it is a bit also in this picture, that you get beautiful particles, especially Q, but it seems to be kind of core shell particles. No, you have something at the surface.
What we have at the surface is the oxide.
Yes, you have the oxide.
Right.
So my question is it possible to tune the thickness of the shell, and what could be the effect of this shell on the optical properties?
So first of all, so thank you for asking this question. The oxide that grows on these nanoparticles is aluminum oxide. It is unique. There are many phases of alumina. It is completely different than any other aluminum oxide that's ever been grown. It has 20% of the density of a crystalline aluminum oxide. So it's it's like a diffuse network. It's amorphous and diffuse. That's why we can do photocatalysis, because the hydrogen molecules go right through the oxide and they interact with the metal and not the oxide. So, it is unique. It turns out it is hard. We thought it would be really easy to grow it of different thicknesses, but we find it's easier to grow other oxides on it than it is to just grow the alumina itself. So we've grown silica and titania on the surface and extended it this way. But it has very interesting properties. You can actually make it catalytic by by doing certain processes. You can kind of design catalytic processes into the actual alumina itself. So it's an interesting aspect of these nanoparticles.
Thank you.
Thank you.
Thanks. We have time for more questions. If you, yeah, over the, Gilles. No, not Gilles. No.
Thank you for this very nice talk full of innovative ideas. I had just one practical question regarding the membrane that you use. Where does salt go actually, and how often do you have to change your membrane?
That's a great question, because people who know about membranes and about these sorts of processes know that scaling can happen, right? So you can have the deposition of oxides and salts onto the membrane and compromise its function. So in this case, the salt is retained on the feed side of the membrane. We find that because it's a thermal process, we don't have nearly as much scaling as one has in conventional membrane processes. But the worst thing about a membrane system is the membrane. So the thing we really want to do is completely get rid of the membrane. And so when people who work in these sorts of fields, all they know about is membranes, and they really don't like it when I say we need to make these systems membrane-free, but that's exactly what we need to do. So we're looking at different designs where we can completely eliminate the membrane, because as you know, membranes they're very fragile, and you would have to replace them every 3 months or every, whatever time, whatever the lifetime is of the membrane. So that's the Achilles heel, and we'd like to move beyond that. Thank you.
Thank you.
Emmanuel, you had a question? Yeah. Yeah.
It concerns when you have described the influence of concentration, with a curve becoming very flat when your solution was more concentrated. It was not very clear to me why concentration should have an influence and what is a phenomenon. Why concentration should have an influence, and what is the corresponding phenomenon that indeed induces a flat curve as a function of wavelength?
Thank you for asking that question. I didn't really explain that very well. So this is really just detector saturation, right? So when we first saw this experimentally, we were sort of, wow, we know that detectors saturate, right? So that's just the data, right? And that's just part of it. It's not the real aspect of things. So looking at more detail, of course, this saturates because the extinction is then off scale for these very large concentrations, right? So the real thing is what you only get when you do the theory, right? The real effect. Thank you for asking that.
Maybe one last question, maybe? No? If not, thanks again for this great talk, Naomi.
Thank you very much. Okay.
And now we have a talk from Peter NORLANDER. Which is it? Okay. So you can also use this.
Yes.
If you want to move.
Yeah. No.
Okay, so first, thank you very much for inviting us here. This is really, we had neither Naomi nor I had been to Troyes before, and we are so incredibly surprised by the beauty and the really wonderful aspects of this city. So we hope to come back here, and I will echo what Naomi said. We hope that you can add RISE to the list of affiliated institutions in your graduate program. So I'm going to talk a little bit about the background to these remarkable photocatalytic efficiencies that Naomi talked about yesterday. And it's going to be a little bit more physical, but I'm going to try to sort of get the picture to you rather than any equations. So how do I switch here? This is... I figured it out. So we are dealing with plasmons. So many of you know what a plasmon is, but I'm going to sort of give you sort of the physical definition of a plasmon. So a plasmon is an incompressible oscillation of the conduction electron in a nanoparticle, because you all know a balloon is, the air in the balloon is fairly incompressible. You push the side of the balloon, it will bulge out on the side. If you fill the balloon with water, it's even more incompressible. But electron gas, the homogeneous electron gas that we have in a nanoparticle, where the electrons are a few angstroms apart, is really incompressible, in particular when we deal with the electric fields that come from light. So it's an incompressible oscillation of the conduction electron fluid. So if you, for instance, displace the conduction electron rigidly in a cubic nanoparticle, you will get a negative surface charge on this side and a positive surface charge on that side. Now, creating these surface charges, as you know from electrostatics, this costs energy. So this accumulation of surface charge provides a potential, a repulsive potential energy. So we have kinetic energy here because we have the mass of the electron gas, and we have the potential energy. So what happens is that if we do that oscillation, it's going to oscillate back and forth. So we have a spontaneous self-sustained oscillation. That, of course, will be damped. Now, more interesting plasmons are going to be sort of spherical and other geometries. So for a sphere, for instance, we have, of course, the incompressible oscillation like this to create a slightly different depolarization field. But the real interesting plasmons for us in terms of light harvesting are dark plasmons. And here is a simple example of a quadrupolar plasmon in a spherical nanoparticle. We squeeze the electron gas on the poles, it bulges out on the equator. Now, this plasmon cannot be excited by a dipole, so no matter how you would put in a dipole here, it could not change the motion here. And this is important. Light is a dipole, so because this is dark, so if we somehow manage to excite it, that plasmon excitation will live for a very long time. Now, then you can immediately see the applications of this, because if we have large surface charges, we're going to have large fields. And these kind of fields, they're called hotspots. And that is what has been used in a lot of contexts for early plasmonics research, surface-enhanced spectroscopies, etc. And it's very easy to understand, just from this model here. If we are driving this harmonic oscillator with the field, this is resonant. We have a driven harmonic oscillator that can be excited into a very large quantum number. And of course, we can use classical E&M when we are dealing with quantum systems that are highly excited. That's a correspondence principle. So in almost everything I talk about today, we can use classical E&M. Okay. Now, the plasmon energy of a nanoparticle depends on its shape. So we've seen many examples of that today. And this is very easy to understand again, because the potential energy of the plasmon, the restoring force on the electron gas, is a Coulomb interaction. And of course, Coulomb interactions are long range. Okay? So in contrast to a quantum dot, this is sort of only mildly tunable with size, the plasmon energies really depend on the shape of the nanoparticle. So here is sort of the scale of plasmon energies. So we have everything is dominated by what's called the bulk plasmon energy. This is just the square root of the range in some units. I don't know what units this is, but it's the conduction electron density over the effective mass of the electron. That's just the scale for plasmon modes. We go to a surface. On the nanoscale, the surface plasmon is a little bit smaller than the bulk plasmon. We go to a sphere. We find that for small particles, the radius doesn't matter, it's the shape, okay? And that the plasma energy will depend on the multipolar order of the excitation. So we're going to deal with dipoles where L is equal to 1. So now we go down to even lower energies. And for a cavity, it's a different dispersion. So that was the status of the field until 1998. And of course, when the nanoshells that were invented by Naomi were first synthesized, of course, this had been theoretically predicted way before, but there was no way of making them reliably experimentally. And almost at the same time, Mustafa El-Sayed and Kathy Murphy developed another type of nanoparticle, the nanorod. So the nanoshell has an aspect ratio defined by the ratio of the inner to outer radius, or the vice versa, doesn't matter. And the nanorod has an aspect ratio determined by the ratio of the long axis and the short axis. And what was remarkable, these particles could now be made experimentally on demand, and that the plasma energies depend on this aspect ratio. You could not, suddenly you had particles where you could have you could place the plasma energies exactly where you wanted. And that is really what's led to the growth of the field of plasmonics. Okay. And again, the last part of my introduction, I'm going to show you plasmons in real time. This is a numerical simulation, and it's going to be sort of a nanoshell in vacuum. And we're going to send in the light pulse on this side, and we're going to monitor as a function of time the electric field amplitude in the direction of the incident polarization. So this is done with realistic, Oh, so let's figure out how can we do this. Oh, let's do it again. And up. Is there a simple way, Renaud, you think? No, I think, okay. So I'm going to, this was only for introduction. So what this movie would have shown you is that as this pulse, sharp pulse, multi-bandwidth passes through, you're going to see that even when the pulse is gone, you're going to see a lot of structure, a lot of electric field. You're going to excite a lot of plasmons because this is a short pulse, it's broadband. It's like taking a hammer and hitting a bell. Okay? The shape of the bell is going to dictate the overall sound you feel. And what I also wanted to see you that as after a few picoseconds, we still have plasmons, but those are high multipolar plasmons that are very dark. Okay, so much of what I tell today is going to be an explanation to why we have this remarkable photocatalysis efficiencies when we use light and hot electrons. Okay, so one of the reasons, a couple of arguments I'm going to make. So first of all, so this is a Poynting vector, a contour plot of the Poynting vector of a plane wave incident on an aluminum nanoparticle. So this is off resonance. So you can see a little shadow on this side. So that shadow is because that plane wave have excited electron hole pair excitations, okay, in this aluminum nanoparticle. It's not the plasmon. We are not resonant to the plasmon, but we have a little shadow because we have created electron hole pair excitations. When we shine light into a finite object, we will always do that. But look here at the Poynting vector when we are on plasmon resonance. So this plasmon resonance sucks in light energy from a volume much, much larger than the nanoparticle. The cross-section for plasmon excitation is several orders, can be several orders of magnitude larger than the physical cross-section, okay? So that's my first argument here. It's going to be that plasmons are extremely efficient light harvesters. And we don't have to cover a surface or a catalyst with nanoparticles. We can put them very dilutely, okay? And in fact, even better, we can put nanoparticles that have slightly different plasmon resonances next to each other and tailor now the plasmonic substrate to for instance, the solar spectrum. Okay. Now comes the important thing. So plasmons they can decay with different ways. Because they are moving back and forth, there is non-radiative decay, because they are exciting electron-hole pair. But because they have a dipole moment, we can also have radiative decay. Okay? Now, by changing the radiance of the plasmon, making it more subradiant or superradiant, we can control the branching ratio. And if you go to dark plasmons, we can have all the plasmons decay by exciting electron-hole pairs, which eventually will be photothermal heating. So now we have an incredibly efficient way of heating up the electrons in the system. Not the ions, but the electrons. So what can we do with this? Well, so this is just a schematic. So we are exciting the plasmon, okay? And that plasmon is now going to decay. And the decay is a quantum process. So in fact, the electron-hole pair excitation you do is the plasmon quantum, okay? So you can create very hot holes and cold electrons, or you can create, this is more common, very cold holes and very hot electrons. Now these hot carriers, they're going to be excited outside the nanoparticle. So you excite the nanoparticle, so you make them more available to the environment. So there's a little details here. I'm not going to talk much about it, but I want to point out, and this is also verified in this publication, that the plasmon-enhanced yield of hot carriers is about 1,000,000 times more higher than for direct excitation. So now we have an incredibly efficient way of creating, of just heating the electrons, okay? So we can do things. So now, just in anticipation of what I'm going to talk, going back to Naomi's talk yesterday, so we showed here that photocatalysis was incredibly more efficient than thermocatalysis in certain cases. So why is that? Well, what's the mass? You take a chunk of metal. The mass of the electrons is about 100,000th of the mass of the ions, okay? Because electrons are so light. So when we do thermocatalysis, we are heating up both the ions and the electrons. But it is only the electrons that do chemistry, okay? So if we have a way of directly heating up only the electrons, we can make that in principle 100,000 times more efficient than thermocatalysis. But the crux is that the hot carriers that we are creating, they are not staying hot forever, okay? So this is the life of everything is substantiated here by calculations, and that was in this paper here. This is sort of a calculation where we depict what happens with these hot carriers. So we're imagining, sort of a plasmon excitation at time equals 0. Now that's going to result in hot carriers, okay, if you have tuned the radiance of the nanoparticle. So now we create a very hot non-equilibrium distribution of hot carriers. And the important thing here is that they're dark, okay? Because what creates the hot carriers is the near field of the nanoparticle. So there is no dipole moment. So these carriers that are created cannot radiate in the decay as they are created, because they are created by a multipolar local near field. But, okay, we have an incredibly efficient electron scattering. So electrons, they scatter, they interact with each other within less than a femtosecond. It's a contact interaction. So these electrons, they can scatter now into bright states, and where they can decay by luminescence. And of course, once the average, but as they continue to electron scatter, there's carrier multiplication. I'm going to show results of that. And eventually, the energy of the hot carriers are going to be within the phonon spectrum, and then they can create photothermal heating. So if it didn't have electron relaxation, hot carrier-induced chemistry would be 100,000 times more efficient than thermocatalysis. So let's quantify the lifetime a little bit. Okay, so this is now a plot of the instantaneous hot carrier distribution in a silver nanosphere. Okay, so this is the hot carrier distribution at 100 femtoseconds. You see, the red here will be the hot electrons, the 0 is the Fermi energy, and the blue is the hot holes. Okay? And this is now the instantaneous luminescence. So you have after 100 femtoseconds, we have some luminescence. And the reason I'm talking about luminescence is that our chairman today, Renaud Bachelot, is a leading luminescence expert in the world. That's sort of, I'm not directly referencing in the paper, but it's something that you should be proud of here. So anyway, so as time goes, you can see we have carrier multiplication, and we have sort of a gradual relaxation of the electrons, and we see a red shift of the luminescence. And this is because luminescence is caused by the decay of hot carriers, and as they relax, you redshift their energy. So you can see that very clearly. Now, you can also see here that, in fact, what I'm showing here is sort of the number of hot carriers in certain energy regimes, okay? So electron-electron scattering is some femtosecond. So, but what is the lifetime of a hot carrier? Well, it's much longer because the electron-electron scattering is elastic, so the electrons remain hot. So what I'm showing here is as a function of time after excitation, the number of hot carriers within these sort of energy regimes. So you can see, for instance, the blue, these very, very hot carriers here, they decay within 1 to 2 picoseconds, but they are filling the lower energies. So we have hot carriers remaining several picoseconds after sort of this instantaneous excitation. So this is going to be very quickly. So the fact that luminescence is caused by decay of hot carriers, now that means that that if we use the CW excitation of the plasmon, is that we will have an intensity dependence of the luminescence. Okay, so very schematically. So here we have a sort of if you imagine a low intensity. Okay, so now the photons are coming in at at rather large temporal spacing. So in particular, if we are sort of at the intensity minimum here, where the decay of the hot carriers is faster than the spacings between our photon, then we have the luminescence is just going to be intensity dependent linearly. But if you are increasing the intensity to a level where, in fact, photons are hitting and exciting the plasmon faster than it takes for the hot carriers to decay, so I'm going very fast here, then we're going to see a blue shift of the luminescence. Okay, and that's exactly what Stefan Link saw. I know I'm going very fast here. So this is a very interesting experiment. So where he actually measures the shift of the luminescence as a function of intensity, and in fact he sees very, very clearly that blue shift with increasing intensity that I was talking about. And here's the theory and the experiment. It very well explains sort of the very, very good agreement between theory and experiments. So before I go into photocatalysis, I just want to highlight the recent collaboration with the Giuseppe Della Valle and Alessandro Alabastri at Rice, and the first paper, Andrea Scirato. So we wanted to more concretely verify the existence of hot carriers. So they did this time-resolved experiment. So they create the metasurface. This is isotropic. So here this has C2V symmetry. So it has a doubly degenerate point group. So no matter what, if you look at this metasurface with regular light, there is no polarization dependence. Okay. So what they did here, they came in with a pulse, okay, and they excited the plasmon, a pump pulse. Okay. Now that plasmon induces an inhomogeneous hot electron distribution. So you will have much more hot carriers here at the edges than here. So this pump pulse has introduced a symmetry breaking, a light-induced symmetry breaking in this particle. And then in a probe pulse with very 50-second sort of control, they are able to show how this symmetry breaking, transient symmetry breaking from the pump pulse eventually disappear, okay, and we revert back to the isotropic situation. And the paper is very clear. It shows this is very significant symmetry breaking. So we create, so this is a real space visualization, basically, of hot carriers and their decay. It's a very interesting experiment. I encourage you to read this paper, take a look at this paper. Okay, hot electron applications. I'm just going to talk very briefly about photodetection. That's how Naomi and I started with hot carriers. And then I'm going to move to photocatalysis, okay? So here was sort of the first paper. Okay, so this is the device fabricated by Mark Knight. So we have n-doped silicon, and on top of that we put a gold nano antenna, and then he covers everything with the transparent conducting oxide, ITO in this case. And he does that because what happens here now, and that was demonstrated by measuring a photocurrent signal here, is you excite the plasmon. So at this wavelength that corresponds to this nanorod here, you create these hot carriers. Okay, and some of these hot carriers will decay into the substrate. We can measure it as a photocurrent, but we have to backfill with electrons because otherwise we're going to ionize this gold nano antenna so that no hot electrons can escape. So we got I'm just showing our work here, but we get photo efficiencies, internal quantum efficiency of up to 10–20%. And the Fabrizio actually got 30%. So hot electrons exist. They are there. Okay, they can certainly be used in photodetector application. But now I want to go to chemistry. Okay, and as Naomi mentioned yesterday, that if you put a molecule on a metal surface, you're typically going to have anti-bonding resonances above the Fermi level and bonding resonances below the Fermi level. Okay, so if you have no hot carriers, okay, you cannot have hole transfer or electron transfer. But if you have hot carriers, you're going to have the possibility for both hole and electron transfer. And the wonderful aspects of chemistry is that the reactivity of a molecule depends on this electronic configuration. So this is now a way, by heating the electrons, okay, creating hot electrons, it's a way of activating the reactants in a catalytic reaction. Okay? And again, I want to acknowledge Emily Carter. I'm not a chemist. She is. And so, but the chemistry I'm going to convey to you today is sort of originates a lot from her. So Naomi has already talked about the initial experiment we did for photocatalysis. It was showing that we could dissociating hydrogen molecule on a gold nanoparticle. And as a physicist, for me, a hydrogen molecule is a helium atom, and that's for a chemist too. It's a closed shell system. Gold has no frontier, it's a closed shell system too. So the ability of dissociating hydrogen molecule on gold is virtually energetically impossible unless you create an H2 minus. Okay, because that electron that comes now as a hot electron will go into the antibonding, the Fespar's resonance of the H2, and there will be Coulomb repulsion, and it will dissociate very easy. So that was a very clear experiment. But it wasn't very efficient. It was a proof of concept, okay? And it made us start thinking. So to have real catalysis, we're going to need a light harvester. We're going to need plasmonic antenna. We can get this enormous cross-section. But we're also going to need sites on this particle where reactants can absorb. Okay? You cannot do chemistry. The hot electrons are always confined to the surface. So you need sort of transition metals to provide the substrate for catalysis. So, and they are here. So how can we combine plasmonic particles with reactors that are sort of have chemical affinity? And this is the antenna reactor concept. So everything I show you from now on is going to be on the antenna reactor. So we are decoupling light harvesting from chemistry, okay? So we have this plasmonic nanoparticle, and then in the near field or on it, we put a catalytic reactor. And this is discussed here, and there are many ways this can be done. Sometimes you put them in contact, in which the hot carriers from the antenna can go in. Sometimes we just put them a little bit away, where where the reactor now, this is dark, they don't absorb light without the antenna, feels a field that drives forces of plasma oscillation and creates electron-hole pairs and hot carriers. This is just to demonstrate the versatility of the antenna reactor concept. So you can, so this is just the paper here. The little grains you see here, that's catalytic materials. And the big scaffold you sit on, that's an aluminum nanoparticle in this case. You can see here, for instance, that there is very little volume of precious catalysts, okay? The amount of iridium, for instance, here amounts to several tens of thousands less of aluminum. So this is actually a very sustainable type of a catalyst. Here's one I'm going to go very quickly here. This is CO2 reduction. So we are forming CO, okay? And at first sight, that seems really stupid. We are taking something that the plants need, CO2, and we are creating CO that people die of, you know? But the nice thing here is that CO is very easy to get rid of. So this paper from 2017, we used an aluminum nanoparticle covered with copper oxide, and we got 4-5% external quantum efficiency to convert CO2 to CO. Okay, and now this is one of the absolutely worst poison. It's not necessarily a greenhouse gas, but it's really, really, really bad. It's, and that's sort of N2O. So that's coming out from agriculture. The ammonia fertilizer will generate N2O. So, and this is something we have to abate, okay? This will destroy the planet as well if we don't, because it really eats up the UV protection we have. Now, it happens to be a great fuel. It's an exothermic reaction, and it actually decomposes. If you can decompose this into the nitrogen molecules and oxygen molecules, you basically have a way of storing air. So being able to decompose N2O in a clean way without forming sort of other types of nitrogen oxides is extremely important. First of all, we abate the N2O, but we could also exploit the chemical energy in N2O. And this paper shows that we can do that very, very well with an aluminum nano antenna covered by iridium reactors. Okay, so now we went more into the antenna reactor concept, and here there is a paper of we established something very important in terms of designing and optimizing catalysts. Okay, and that is that we can actually, so you all know this is Arrhenius equation. So chemical reactions proceed with sort of this type of rate reaction. Of course, chemistry in general is a coupled equations, but each of the sort of intermediary steps proceeds with this activation energy. So to increase the rate, you can increase the temperature, okay? But of course, that's very costly because you're wasting energy heating the ions in the system. Or you can decrease the activation energy. When you do photocatalysis, you do both, okay? Because you are actually changing the temperature. You have some ambient temperature in the catalyst. Now then you have you illuminate by an intensity, and you have some kind of photothermal efficiency here, and then there's some radiative term. So when you do an experiment with photocatalysis, you have to make sure to compensate for this, the photothermal heating, because otherwise you're going to underestimate the activation energy. So, and of course you can do that. There are 4 parameters here. So if you do the measurement of the rate for 4 different ambient temperatures, you can eliminate the quantities. And you can get now this very fundamental concept, the light-dependent activation barrier. So this is the intrinsic activation barrier. It depends on the intensity and wavelength of light, okay? And the reaction we are looking at is ammonia decomposition. So this is sort of at this moment, the most likely way of storing hydrogen is as ammonia. So hydrogen can explode. Ammonia smells bad, but it doesn't explode. So this is actually a way of storing ammonia. So this decomposition reaction is extremely important. It's one of the most well-studied chemical reaction in surface science, dating back tens of years. I'm not going to talk much about it, but there is 2 reaction steps. So these are coupled equations. Here is the NH breaking with an activation barrier of 0.2, and then the final barrier here is the associative desorption of N2. So N2 forms a nitride, so it's binds. So that's sort of the rate limiting step. First observation when we do photocatalysis here is several orders of magnitude more efficient. than thermocatalysis. So that's important. And here is now the result of 1.5 years' work of Lin Anzhou. So he did this fitting of the rates, changed the ambient temperature. In addition, he measured the temperature of the substance. And he extracts now the light-dependent activation barrier. So this is intensity, this is wavelength. So in the dark, okay, there's no wavelength dependence, of course. The barrier is 1.2. Now, if we go to 550 excitation, and at this intensity, the barrier becomes 0.2. So what hot carriers have done, basically, is they have removed, they have eliminated, the hot carriers have eliminated, they have promoted this associated desorption of N2. They have not been able to do this, but we have been able to go from an activation energy of 1.2 to an activation energy of 0.2. If we were to do that in thermocatalysis, it would be a factor of 6 higher temperature, everything would melt, okay? So the photocatalysis here is an incredible transformation of the ability of doing this reaction in sort of moderate condition. Fluorocarbons, they are horrible poisons, okay? Ozone, again, is a problem. In fact, many air conditioners in the old had Freon. This is really bad. Now they have different types, but we still have a lot of hydrofluorocarbons around. So here we show that a palladium-decorated aluminum nanocrystal is very efficient in destroying the fluorocarbons, okay? I don't have time for the details. So Naomi already talked about this really surprising discovery that for the H2 dissociation reaction, that the octopods were so much more efficient than these other type of nanoparticles. Okay, so we compared here octopods, cubes, and something else, octahedrons, I guess, nanocrystals. We can see an enormous change in activation values, enormous change in efficiency. And it's interesting that, in fact, you can almost see that this is consistent. So this is the heating. So the octopods, they have blue curves here. You illuminate them, they heat, but not as much as the nanocrystals. And this is consistent with them being much more efficient because we are creating these hot carriers. Now they do catalysis. So some of the hot carrier energy is going away to the chemical energy. That's why they will actually heat less. So although they heat less, they are much more efficient in catalysis. And this was all modeled. We could understand it. Here's an interesting paper too. Again, we can do these kind of reactions, or Naomi can do these reactions with kind of any chemical. We like the H2 dissociation because it's unambiguous. If that dissociates, it's hot carriers. So here we actually showed, and this was copper nanoparticle now, that we got the external quantum efficiency larger. Is this me? We got an external quantum efficiency larger than 100%. So why is that? Well, this is hot carrier, is carrier multiplication. So dissociate this, the H2. You don't need a high hot electron because you can do successive vibrational excitation. So as the hot carriers relax and you get more of them but with lower energy, the energy is still plenty for inducing the dissociation of the H2. Okay, so now also this was mentioned in Naomi. This I think is perhaps the most important application apart from ammonia decomposition, that is to make hydrogen, okay, in a sustainable way. So here, in this paper here, we did use methane dry reforming. So this is the chemical reaction, okay? And this is done industrially too. The problem with any carbon-containing chemical reaction like so is coking. So if you use sort of a standard ruthenium catalyst, which is what people are doing, carbon some carbon will sit here, and of course if there is a next neighbor carbon, because the carbon has a valence of 4, you can basically polymerize. You cover the catalyst by a carbon film. It's called coking. And then you have to stop the process. You have to heat the chamber, waste energy, get rid of the coke, and then you can restart the process. So here we use an antenna reactor, but with single catalytic sites, single ruthenium sites. Okay, and I will show you we don't get coking. So here is the stability of this reaction as for different amount of ruthenium here. And for instance, we go to this yellow line here. Is stable over 16 hours. There is no coking, okay? And if you do the analysis of elemental composition, this is the limit that we have single atom. So that's the first step. Anytime you want to abate carbon, you have to make sure to you prevent coking, and a single catalyst like this is very cheap, and it's also very efficient. So here is a little bit more. Now, in thermocatalysis, so here we are destroying two of the worst greenhouse gases, and we are forming one of the most useful compounds in chemistry, including hydrogen. Again, carbon monoxide we can remove. We can just bind it to some capture metal, so that's not a problem. And we can also use it, of course. Now, if you do the thermocatalysis, you have a very undecided side effect, okay? Some of this hydrogen can back-react with the carbon dioxide, and you form water. Of course, you form CO, it's not a problem, but you get less hydrogen, okay? And so when you talk in the industry, when you talk about the efficiency of a catalyst here, you did talk about the selectivity, which would be the ratio of H2 over CO. So if you have no reverse water gas shift here, you will have a selectivity of 1. Let's compare efficiency and selectivity of in thermocatalysis and photocatalysis. So this is thermocatalysis, okay? First of all, you can see you still have coking here. So the efficiency goes down. This is coking. Selectivity is really bad. You're getting sort of only perhaps 90% of all the hydrogen you produce goes back into water. Here is the photocatalyst. We have an order of magnitude larger efficiency. We have no coking, and we have a selectivity of 1. We have no reverse water gas shift here. So we're actually producing very, very good hydrogen. And energy efficiency is remarkable, 35%. You can never get that in thermocatalysis. Now, so this is, although I love this reaction because we are destroying CO2 and methane, that's really good. Industrially, you could not make a living out of this because there is simply too little CO2 available. You could do this on a chimney or something like that, but for large-scale production of hydrogen, there is simply still too little CO2 in the atmosphere. So instead, you do methane steam reforming, okay? And that is now destroying methane. This is actually a very bad greenhouse gas. You don't destroy CO2, but you're doing this reaction. So you produce, again, a little CO. You can filter away. You can bind it, mineralize it, but you produce a lot of hydrogen. So this is the way hydrogen is produced, and also with electrolysis. I'll show you that later. Conventional thermocatalysis, high temperature, high pressure. Large, expensive, you use fossil fuels because you have to heat it. Worst thing, cooking. You have to turn this off, heat it up to get rid of the carbon and restart it. So the catalyst regeneration is a big problem. So the plasmonic photocatalysis here we can do in a plastic container, low temperature, pressure. We can use sunlight or we can use LEDs, okay, because they are very efficient. One of the most important things with this is we can do hydrogen on demand. We don't need to store hydrogen in a big tank that could explode. You can basically put this kind of generator, the reactor, at the gas station, and when the car comes in, you turn it up, okay? You can do it on demand. And the movies Naomi showed yesterday, this is the company now with more than 40 employees that is actually commercializing this. And why is that company getting funding? Because you can do it very cheap. So here is this is my last slide here. This is the sort of a breakdown of hydrogen production. So electrolysis, okay, first of all, 1 kilo hydrogen is equivalent to 3 kilograms of actually diesel. Now, and the fuel prices in USA now is outrageous. So a gallon of gasoline will be $2, okay? So, but that's likely to go up. So this will make it even more favorable. So in the cost per kilogram for electrolysis is $8 a kilogram. Now, if you transport hydrogen, okay? At least in the States, you have to have special truck because it can explode, okay? So yes, delivering hydrogen adds another $10 per kilogram to the cost. Now, so what people have been thinking about is having methane steamer forming on site. This would be about $6 a kilogram. But then having large capex, large equipment, high pressure, high temperature, and poor energy efficiency. So the kind of on-site plasmonic methane steam reforming we can do will put down the price at $120 and also with much less capex. So I think I'm going to stop here, just to hope this has been a little bit more technical than perhaps what you wanted, but I wanted to explain there are solid physical principles behind this remarkable efficiency of photocatalysis, and the center to all of that is the antenna reactor concept, okay? Where we can use cheap, abundant materials as plasmonic antennas, and we can use a tiny amount of more precious transition metals and get very efficient catalysis. And I want to thank the red. Now we should really have a bigger font here, but I couldn't fit that in. That the red people here are the people who sort of been involved in this. So with that, I thank you for your attention.
Thank you so much, Peter, for this great talk. I guess we have many questions. Yeah.
Yeah, thanks a lot for this talk. So I have a question concerning how do you control the activation energy? Yes. So is it something that is similar to polytonic chemistry, for instance, or very different?
So first of all, we don't know exactly. Okay, so if you go back to our science paper, which was sort of here. So in this paper, we put forward two possibilities. Okay, so and that could be, it could either be an electron transferring into an antibonding orbital, in this case then of the nitrogen, because the limit, what we control here with light is this barrier, and that's the rate limiting straight. So it could be an electron transferring into an antibonding state. This is a closed shell system. So any electron you put in a closed shell system is going to be, lower the bonding energy. But there could also be, but in this science paper, we also put forward the possibility that the hot carriers are actually exciting, in this particular case, the nitride. So we have here ruthenium. So we have one nitrogen on one ruthenium and one nitrogen on the next ruthenium, okay? This was not a single atom catalyst. So the hot electrons come in and they are exciting a vibrational quantum. Okay, and a nitrogen ruthenium bond has perhaps a vibrational quantum of 60 millivolt. I'm guessing, I don't remember, but there's this compelling reason for that, because a hot carrier can go in and excite that vibrational bond, but it doesn't destroy the electron. So the phase space you have, so that any hot electron with an energy higher than that vibrational quantum can go in and kick it up, okay? And vibrational relaxation is very slow. We have a lot of hot electron doing it. So the problem, the question you ask is something we have been struggling with for many years. Doing ab initio theory on excited states is basically is impossible. Okay, we can approach, but density functional, for instance, is a ground state theory. So we don't. I think the results are so good. So I can tell you, honestly, we don't know exactly. So in this paper, we had two models for the hydrogen dissociation. We know it is an excited state because the hydrogen, even a quantum chemist can do that well. But doing a nitrogen or an oxygen or a chlorofluorocarbon, they cannot do. So that's my answer.
Yeah, thank you. It's very spectacular. Thank you.
Can you tell us more about the relationship between the dark nature of the states and the multipolar nature?
Yes.
Because this
yes.
is, I asked the question.
It's your work. It's
I ask the question because sometimes, depending on people, the definition of dark states can be different.
And it's actually because Alex Bouhelier is here too. He's doing some great things on fluorescence. This is important. Okay. So the hot carriers are created by an electric field. It's an electric field excitation, but it's a curved electric field. There's very little dipole component, and it's a near field. So each of these hot, so this excitation here, so suppose this hot carrier, you created a hole here and this electron here. The delta L here is not 1. Delta L can be 25. Okay, meaning that this hot carrier cannot decay. Okay, so a dipole can excite. So the reason we have luminescence is because we have bright states. We are connecting states, we are connecting electrons with hole that has a difference in angular momentum of 1. Okay? If we have created this electron of hole with a non-dipole, like a near field, it cannot decay. But what saves the day in terms of luminescence is that electron scattering is very fast, okay? So we create a fairly substantial density of hot electrons. Now that's a contact interaction, okay? So a contact interaction means there is no conservations, okay? So you can come in here with sort of a high angular momentum and that collides with a high angular momentum. Yeah, you can come out with 1, you can come out with anything. And the moment you're starting to form now electrons that can be connected, where the delta can have a transition delta L equal plus minus 1, going from an electron to a hole, then you can have luminescence. Okay? Of course, the story is more complicated because you cannot have luminescence efficiently at arbitrary wavelengths. So for luminescence, you have a transition matrix, but you also have the photonic density of states. Okay, so that's this very modest plasmonic nanoparticle we did here. We see an overall blue shifted intensity, but blue shifted intensity, but the luminescence is still peaked because it's really dominated by the photonic density of states. And for a nano rod, I think this was a nano rod. This is the longitudinal resonance. So.
More question, Alex?
Thank you, Peter. I have actually 2 questions. The first one maybe is following your comments. How do you take into account the interaction between the hot electrons and the surface? And the surface of the particles.
Oh yes, okay. So this is a quantum. So this is actually a full quantum mechanical calculation. Now I'm the first. So this is density functional. This is time-dependent density functional. And it's also a Jellium model. There is no band structure here. So the surface, the very surface is included because it's a finite nanoparticle calculation. Mm-hmm. We think this is qualitatively correct. We are not sure it's quantitatively correct, but the surface is completely included. And if you look, so here was luminescence we calculated. If you look at the optical spectra for these small particles, we see the quantum size effects that people, we see a broadening of the plasmon resonance when the particle gets so small that the mean free path of the electrons it becomes of the order of nanoparticle. So that part is included. There are many other things that are not included.
Okay. And the second question is, you were in the second part of your talk, you did an extensive survey comparing thermal catalysis to photocatalysis.
Yeah.
But you were you didn't talk too much about what kind of a laser or what kind of a source.
So
what kind of a light source
that
were used in all this study? Are they, expensive lasers or are they LEDs?
So first of all, it sounds like I did the experiments, but let me assure you, Naomi keeps me at a very long distance. So we do many of these experiments with tunable lasers. Now the CCG that we are doing for the real photocatalysis, that's with LEDs. And in fact, the LED manufacturers, they're so excited about this opportunity. So they make the LEDs exactly at the wavelength we are needed, because they are anticipating markets. So, but in the lab, it's all sort of titaniums and phianium. I don't really know, but Naomi can tell you afterwards, okay?
I'm sorry, just for convenience within the laboratory in order to get the light into a cell and so on, we use lasers. But we have also shown with solid state sources, with LEDs, the reactions are often even more efficient.
Maybe one last question. Yeah.
Yeah, thank you. I had a question about regarding the last part of your talk when you were speaking about the different process for H2 production. To give some context for those who wouldn't know, a problem with the classical way of producing H2 is that it's highly emissive on GHG emission. The order of magnitude is something like 10 kilograms of CO2 for 1 kilogram of H2 produced. Mm-hmm. And I was wondering on this process with Plasmonic, you didn't specify the details of the reaction. Is this just a lowering of the temperature? So the emission is basically kind of the same, or is it something more?
This is a great question. Okay, so first of all, I'm not a complete expert on these things, but to get these incredible efficiencies that we demonstrate in our papers and the company demonstrated too, we need both light and heating. Heating is always good, okay? So the question now, what I'm showing here, what is remarkable about also methane steam reforming is that we are really not producing any CO2. We really so this is dry reforming. So we are truly producing CO. And I'm really not an expert, but my friends at the company, they tell me about this. So either you can actually, there are ways, I think they say calcium powder and so on, where if you put in the CO there, okay, the H2 is not going to react with the calcium, but the CO will. Okay, when they do these experiments that I showed the stats for, there is no CO emitted, there is no CO2 emitted. I mean, this is really important. There is also filters, because in fact the chemical industry can use CO. Okay, this is part of syngas, and so H2 is really small. Okay, because I mean it's really like a helium atom because it's only bonding electrons. The CO is much larger, so there are filters to actually get rid of CO. And I'm not a chemical engineer, but this is not regarded as a problem here. But I know I didn't answer everything you wanted, but I'm a theoretical physicist, so.
Thank you. So I guess it's time to conclude. So before handing up, I just would like to thank warmly the volunteers, the students, please. Thanks for your. We have many students whose help has been very useful. So thanks again for these great talks, and thanks for your. So now we have a lunch buffet at the first floor of the M building. So thanks again for your participation, and have a great day. Have a great afternoon. Thanks.